Hello, class. Today we're going to be introducing Chapter 4 on vector spaces. So vector spaces brings together a lot of what we learned so far about how vectors and matrices relate to one another. This introductory example is located in your textbook at the beginning of Chapter 4, so I encourage you to read it. It discusses an application of vector spaces in terms of flight control. So this particular application is looking at how the Columbia used linear algebra to work with their control systems. So again, you can read this on your own in the beginning of Chapter 4. Today we're going to focus on 4.1 on vector spaces and subspaces. So vector spaces and subspaces. First, we're going to define a vector space. So a vector space is a non-empty set V. So vector spaces, they generally give the capital letter V to denote a vector space of vectors. And within the vector space, they define two operations, addition and multiplication, by scalar quantities. And if you have a vector space, the following 10 things will be true. So if you have, for example, two vectors in the space, the sum of those two vectors must also be in the space. So it says the sum of u and v are going to be in the vector space V. So what that is called for, number one, is closure under addition. So if you have two vectors in there and you add them together, that vector that is generated is also in the vector space. We also have commutativity here, that adding vectors in any order doesn't matter, which should be a quantity or a quality of all vectors. So that's kind of a given. This is the associative property of vectors, meaning notice the order of the three vectors, u, v, and w, does not change, but the order in which you group the addition changes. This, you're grouping the first two vectors together, adding them, take that result and adding it to w. Here you're taking the last two vectors, adding them together, and adding that to u. That is the associative property, and this is going to be true for all vectors. Okay, so these you don't really have to prove outright, because if you have vectors, these are going to be true. Closure, that isn't guaranteed, so that's one you got to look out for. So the zero vector has to be in V. So if the grouping of vectors does not contain the zero vector, then it is not a vector space. So zero vector must be amongst the vectors listed in the vector or in the space for it to be a vector space. Okay, so that's a requirement. Additionally, you have to have negative u included in u, and that's pretty much always going to be the case if you have a span, because spans include all scalar multiples of the vectors. So this is going to be true if it is a span, but if it's just a listing of vectors, both u and negative u have to be included in order for it to be a negative, or in order for it to be considered a vector space. Any scalar multiple of u must be in V, so it must be closed under scalar multiplication. This is going to be true for all vectors that you have a distributive property if you distribute a scalar quantity. And this just states that for multiplication of the sum of two scalar multiples, that you have a distributive property there for that. So in 7, you're distributing a scalar over two vectors. Here you are distributing a vector over two scalars. So these two are going to be true of all vectors. So those are kind of gimmies. This is also a gimme. This is the associative property of vector multiplication by two scalar quantities in one vector. That's also true for all vectors, that's going to be the case. And then lastly, for it to be a vector space, 1 times u would have to equal u, which is going to also be true for all vectors. So things that aren't going to be always true and things you have to check for to prove vector space is that the opposite of the vector is in vector space. But really, that's going to have to be true if 6 is true. If 6 is true, meaning it is closed under scalar multiplication, that means that negative u has to be in it if u is in it, because that's just scalar multiplying by -1. So if 6 is true, you're going to have 5. If they are vectors, 7 through 10 is going to be true. The sum has to be in V. That's closure under addition. That you have to check for. This one you have to check for as well, because if they just list a group of vectors and say, does this form a vector space, you have to check that it's closed under addition. You have to check that the 0 vector is in that group of vectors. You also have to check for the closure under scalar multiplication. And if you have 6, you're going to have 5. So really, you don't need to check for 5 separately, unless you want to. It's up to you. So that is what makes a vector space, is if the vectors have these 10 axioms. Also, as a result of this, you get the following properties: that multiplying by 0, a vector by 0 yields 0, 0. Multiplying a scalar quantity by the 0 vector, you get 0. And then just this particular scalar multiplication by -1 is the same as -u, which is the vector in the opposite direction. So these are all true for every vector. Okay, so let's take a look at example 1. Example 1 dives into the geometric representation of vectors. And hopefully you'll get that by looking at the picture and just hearing the description. Let V be the set of all arrows or directed line segments in 3-dimensional space, with 2 arrows regarded as equal if they have the same length and point in the same direction. And then they define addition by the parallelogram rule, which we learn about when you learn about vectors. And scalar multiplication is changing the magnitude of the vector. So if it's 3v, it makes v 3 times as big. And so this is creating a geometric representation of vectors that we should all be familiar with. And they give us a little diagram of what v would mean, what v multiplied by the scalar 3 would mean, and then what -v would be. So if you define v to be an arrow in this direction at this magnitude, this is what 3v would be, this is what -v would be. So that's just kind of demonstrating what is going on with the geometry of the vectors. And this is exactly like the geometry we learned about vectors way back when. So if we want to determine if this is indeed a vector space, so if V forms a vector space, this is how we can consider it. So the definition of V is geometric, as I stated, using concepts of length and direction. We don't talk about what the actual numbers are that make up the vector. We're not calling V 1, 2, 3. We're just defining it geometrically. So what we can do is then, given that definition, consider that the 0 vector, which must be included, would be defined as a single point. So geometrically, the 0 vector would be a single point. The negative of V is -1 times V, which is defined because scalar multiplication is defined. And so this would define axioms 1, 4, 5, 6, and 10. Looking at axiom 2, that would be the commutative property of vectors. This defines V plus U. This defines U plus V and V plus U. And you can see that those two are equivalent. So we have geometrically proven the commutativity of vectors. And then here we have 3 represented, axiom number 3, which is the associative property of vectors, and it states that u plus v plus w equals u plus v plus w grouped differently. And let me just show you on the diagram what that would look like. U plus v plus w is right here. U plus v plus w is the vector addition of those 2 vectors. So your resulting vector is this red one. U plus, that's the resultant here. That's u plus v plus w. Now if you look at u plus w plus v, that is this path. U plus w plus v is the yellow side of that equation. So here's u plus w plus v. And notice the resultant vector is the exact same thing if you connect head to tail. So this is the red one and this is the red one. So that geometrically shows that the associative property is true when you consider the geometric representation of vectors. So that is axiom 3. We already addressed the 0 vector, which is axiom 4. And then we could also hop into 8, 7, 8, and 9, which are just proving that distributive property of the scalar over the 2 vectors and the 2 scalars over the 1 vector. So those we could draw diagrams for as well. But hopefully you're getting that the vector space is defined both geometrically and algebraically. So along with vector spaces, we have vector subspaces. A subspace of a vector space V is a subset H of V. Okay, so note H is what is used to define a subspace. V is used to define a space, a vector space, and H is used to define a subspace. In order to determine if a subset of the vector space is a subspace, you only have to look at 3 of the axioms. So essentially, let's say they give you a vector space, which is made up of the span of like 6 different vectors. And then you pick out 2 of those, and you want to see if that forms a subspace. What you're going to look at is the 0 vector included? Is it closed under vector addition? And is it closed under the multiplication of scalars? And if those 3 things are true, you have defined whether H is a subspace of V. So that is how you define subspace, is through those 3 properties. You don't have to go through all 10 because you already know that V is a vector space and you're just plugging vectors out of it and trying to see if they have a space themselves. So those are the 3 properties of a subspace. So these properties guarantee that a subspace H of V is itself a vector space. Every subspace is a vector space, so it can stand alone or it can be part of the whole. And also every vector space is a subspace of itself. Okay. So I don't know if you guys remember us talking about sets and subsets, but this language is the exact same thing. Every vector space is a subspace of itself. Okay, so if I said, oh, let's look at this vector space, how many subspaces can it have? You would consider the vector space itself as one of the subspaces. Just kind of a fine point there. All right, so let's take a look at this example. It says, given V1 and V2 that are in a vector space, and we define H as the span of V1 and V2, we're going to show that H is a subspace of V. Now remember, a span means you have scalar multiples of V1 and V2 that are added to each other. Or in other words, you can say it is a linear combination of V1 and V2. Okay, that is what a span is. So let's look at how to prove that that is a subspace. The first thing we have to prove is that if you take a span of V1 and V2, you can get the zero vector. So the way you get the zero vector is by doing a linear combination of V1 and V2, but the scalar quantities are both zero. That ensures that the zero vector is in H, the subspace. To show that H is closed under vector addition, you have to show that if you add a linear combination of V1 and V2 to another linear combination of V1 and V2, you get something that would also be in the subspace. So what we can do is define U as the sum of some scalar quantity times V1 plus another scalar quantity times V2. So that's one vector that will be in the span. And then another vector that will be in the span, we'll call it W, is another scalar, T1 times V1 plus T2 times V2. So these two vectors are in the span because they are made up of a linear combination of V1 and V2. So if we add U and W together right here, if we sum those together, we have to show that that quantity is a linear combination of V1 and V2 because that would mean it is in the span. And if it is in the span, that means it is a part of the subspace because that is how the subspace is defined. So what we can do is show the addition of these two vectors. And then what we can do is group the coefficients or the scalar of V1 together and then the scalar of V2 together. And then you know this is a scalar quantity and this is a scalar quantity. And since we're now writing this as a linear combination of V1 and V2, that means it must be in the span. And if it is in the span, it has to be in H because that is how H is defined. So what this particular proof does is it shows that H is closed under addition, which is one of the requirements. It's actually the second requirement of proving that you have a subspace. Lastly, you have to prove that it is closed under scalar multiplication. So it says if C is any scalar, we can write U as the following. And let's take a look. We defined the vector U up here as S1V1 plus S2V2 because it is going to be generated by doing a linear combination of V1 and V2. So if we take that quantity and multiply it by a scalar, we have to then show, and in this case we're using the scalar C, we have to then show that it is in the span. So what we can do is multiply, factor, and then we have that V1 equals CS1. I'm sorry, V1's coefficient or scalar quantity is CS1, and V2's coefficient or scalar quantity or scalar multiple is CS2. So this is also in the span. And it is in the span because if we multiply by a scalar quantity, it is still going to be a linear combination of the two vectors that were given to create the span. And so this demonstrates closure under scalar multiplication. And so you have done the first property, you have proven the second property, and you have proven the third property. So the zero, closure under vector addition, and then closure under scalar multiplication. And that is what it takes to show that V is, H is a subspace of V, where H is defined as the span of the vectors V1, V2. Okay, so that is that proof. So you can have a vector subspace that is very small. It can't contain no vectors, but it can contain one vector. And the one vector it must contain, if the subspace is that small, is 0. So it has to contain the 0 vector, or else you have violated the very first property of subspaces. So if your subspace only contains one vector, it is just called the 0 subspace because that's the one it must have. And as the term linear combination refers to any sum of scalars of multiples of vectors and span V1 through VP, denotes all the sets of vectors that can be written as linear combinations of V1 to P1. All right, so theorem 1 gets into what we just proved. Theorem 1 states if you have vectors that are in a vector space, then the span of those vectors are a subspace of V. And you can use the language, the span V1 through VP is the subspace spanned by those vectors. So what we're doing is stating that a span is a subspace of those vectors, okay? And given any subspace H of V, a spanning or generating set for H is a set V1 through VP in H such that H equals the span V1 through VP. So some more language regarding how we can create a subset or a subspace of a vector space using a span. All right, so let's take a look at an example. This one states, for what value H will Y be in the subspace of R3 spanned by V1, V2, V3? Now, this is a problem we've done many times before, but now it's just using the language subspace. So it's asking, can I generate Y, or how can I generate Y through a linear combination of V1, V2, V3? So what must H be in order for Y to be in this span? So let's take a look. Sorry. If we want to know if it is in the span, we need to determine, or for what H values it will be in the span, what we need to do is some elementary row operations to determine for what values of H Y would be in this span. So essentially, we are figuring out for what values H must be for this to be a consistent equation. So what I'm going to do to solve is I'm going to do, let's see, I'm going to get to echelon form. So I'm going to do 2R1, let's say plus R3. So then we have 0, 3, -3, and I think this is not -3. and then we would do negative 8 plus h. So that's 2r1 plus r3. We could also do r1 plus r2. And so this is going to be algebraically equivalent okay, and you might note that we have a scalar multiple here. One row is a scalar multiple of the other row, except for what is on the right side here. So I'm going to do r2 minus 3r3. So here I get 0, 0, 0. Okay, I think I have a little error here. I think this is a -1. This would be a -1. So that would be a +3. Okay, so we'll note that if I do this, I get 0, 0, 0, and -5 plus h. So looking at this row, in order for V1, V2, and V3 to create, using a linear combination to create y, h would have to be 5. So that is how we can get y into the span, is if h equals 5. So what I did is I created a augmented equation, and I solved for h, looking for a consistent system. So that is how you determine what values of h will allow y to be in the span. Okay, we're going to do a couple practice problems. So the first thing says, show that the set h of all points in R2 in the form 3s comma 2 plus 5s is not a vector space, by showing that it is not closed under scalar multiplication. So what that means is that if we pick, let's say, if s equals 1, let's say. So if we take a look at this point, which is 3s comma 2 plus 5s, and consider it for s equals 1, you get the point 3 comma 7. Now, a scalar multiplication of that point, because it needs to be closed under scalar multiplication, would be the point 6 comma 14. So what I'm asking now is this in h? So h has to be points that are in the form 3s comma 2 plus 5s. Okay. Now I'm asking, is it closed under scalar multiplication? In other words, is 6 comma 14, can it be written in this form? And the answer is going to be no, because if s equals 2, for example, you would have 6, 12. But what we have is 6, 14. So since it is not closed under scalar multiplication, it is not going to be a subset of all of the points in R2. So this proves it. It cannot be written in this form. Therefore, it is not closed under scalar multiplication. Okay, so that is how you prove that. Also, hopefully you saw right away that the 0 vector wouldn't be in this, because if s is 0, you get 0, 2. And if s is -2/5, you'd get -6/5, 0. So either way, you can't get to 0 if the points have to be in that form. So this, but they didn't ask that. They said, show that it's not closed under scalar multiplication. So we did that. All right, I'm going to have to go ahead and erase so I have room for number 2. Number 2 states, let W equal the span of the vectors W1 through WP, where W1 through WP are in a vector space V. Show that VK is in W, where K is some value between 1 and P. So essentially, if W is in the span, or if W is made up from the span, that means W is made up of scalar multiples of V1 plus V2 plus V3 plus VK all the way to VP. So let's call VK some linear combination of, and I'm just going to use the scalar quantity C, so C1 V1 plus C2 V2, so a scalar multiplication. I'm going to throw K here. We don't know exactly where it is. I just know it is between 1 and P. And then I'm going to go to then CP VP. So if our span is what defines W, span of vectors V1 through VP, that is what defines W. And I want to show that VK is in W. So I have written VK as a linear combination of those vectors. To show it is in W, all you have to do is show that VK then can be written by calling the following. So VK can be generated if C1, C2, C3, etc., and through CP are all 0, and CK equals 1. So that is how we can show that VK is in W, because VK can be found by doing a linear combination of vectors V1 through VP. And if all of these are 0, 0, 0, 0, and this is 1, we get VK. So there it is. We have shown that it is in the vector space. All right, that is all for today. Here's the homework. And yeah, hope you guys are good with this. And if not, just give me an email and ask me some questions. All right. Happy mathing.